Hi, my name is Julia Wilkins, and I'm going to be talking about self-supervised multi-view learning for disentangled music audio representations. This work was done in collaboration with Saban Ding, Magdalena Fuentes, and Juan Pablo Bello at the Music and Audio Research Lab at NYU. When dealing with multiple modalities of data, or even multiple views of the same modality, contrastive learning is a popular strategy used for representation learning. In contrastive learning, you train a model to learn a shared representation space for these two different modalities. This has a key downfall, which is that the learned representations focus on shared information across views, missing valuable information unique to the different modalities of your data. In audio, rich attributes such as timbre, frequency, and amplitude are likely to be entangled in this paradigm given a single shared representation space. We aim to address this challenge in this work. We use a multi-stream VAE architecture for our model. The input to the model is a pair of audio waveforms transformed into log-mel spectrograms. Crucially, the two audio files have the same timbre or waveform type, but different frequencies. We pass this pair of spectrograms to a shared encoder, where we then learn distributions that are unique to each input, as well as the shared distributions are the product of experts' method. We concatenate each private latent with the shared latent and send this to the decoder, which learns to reconstruct the original pair of spectrograms. Overall, we aim to incentivize the model to encode timbre information in the shared latent and frequency information that's unique to each input in the private latent spaces using this architecture. We train our model using an adaptation of the beta TCVAE loss to the multi-view setting. The objective is a combination of maximizing the reconstruction accuracy and minimizing a decomposed version of the KL divergence designed to better incentivize disentanglement. The KL term is made up of the mutual information term, encouraging retained information between the latents and respective inputs, the total correlation term, which encourages independence and sparsity within latent dimensions, and the dimension-wise KL term, which further encourages Gaussianity of each latent subspace. Each of these terms are carefully weighted using alpha, beta, and gamma as shown here. In terms of results, here we show a matrix of mutual information between the private and shared latents and the generative factors, timbre and frequency. On the x-axis, you'll see the different dimensions of the latent spaces. So we train our model with 8-dimensional latent subspaces, and you'll see 8 dimensions here. Overall, we're able to show that timbre information is highly concentrated in the shared latent space, and frequency information is more prevalent in private, though not to the same extent as timbre in shared. We take this a step further in downstream classification tasks. We use our trained encoder as a feature extractor, experimenting with using each of the different latents as the embedding, to then train a lightweight classifier on top of for timbre and quantized frequency classification. We show that timbre classification does very well when using the shared latent, and frequency classification using the private versus shared latent is better. We also perform an ablation to better understand the effect of each of the decomposed KL divergence terms. We train our models with reconstruction error and varied weights of each of the terms independently, measured in terms of downstream classification performance. Ideally, here we would want to see that for timbre classification, the shared bars in blue are higher than that in red, and the opposite for pitch classification, where we hope that private representations in red are better for pitch classification than shared. We found that alpha and beta here did not positively impact disentanglement, but the weighting of gamma, which is the core normalization term that encourages Gaussianity across latents, had the most positive effect in terms of this trend. Finally, we show a UMAP dimensionality reduction visualization of the embedding spaces per latent, colored by timbre or waveform type. The private and combination of latent spaces doesn't show particularly strong clustering trends here, though we see some emerging clusters in the center and around the perimeter when using both latents. The shared latent space clusters super well by timbre, showing that timbre information is highly prevalent in this subspace. We can also see that the sine wave embeddings are the most distinct from the other 3 clusters, even in the representation space, likely due to sine waves lacking in harmonics versus the others. It was really cool to see this trend at the representation level. In conclusion, we've presented a novel architecture for disentanglement of view-specific and shared latent subspaces for timbre and frequency disentanglement in a controlled audio setting. Please come to our poster to learn more. Thank you.